So today we're going to look at how to do calculations from a titration curve. And you don't really have to have the titration curve to do that, but it kind of helps give you a roadmap of what you need to do at which places. So the problem that we're going to work is loosely based on example 16.5 in your textbook. That's on page 737 to 739. I've added a couple of points to it, so it won't be exactly like that, but if you want to refer back to what they've done, then of course you can do that. So here's the question. It says calculate the pH in titration of 25 milliliters of acetic acid by sodium hydroxide after the addition to the acid solution of several of these. A, 0 milliliters, so before anything's added. B, 10 milliliters of the 0.1 molar base solution. C, 12.5 milliliters of the 0.1 molar base. D, 25 milliliters, and C, 35 milliliters. And I added in here also the Ka for acetic acid is 1.8 times 10 to the negative fifth. You'll need that information. So when I have a problem like this, the first thing I want to think about is what's happening in the solution, in the beaker, at each step along the way. And that tends to be what trips people up. You want to do the same thing all the way through. And for this, you just can't. So I'm going to kind of think about the pH curve for this. So here's my curve. Before anything is added, that's point A that it's asked me about. At 10 milliliters and at 12.5 milliliters, I'm in this buffer zone that we've talked about. The 25 milliliters is the equivalence point. So when you've got a problem like that, if you can kind of figure out that equivalence point, that's going to help you know what to do along the way. And usually they're going to give you that calculation to do at the equivalence point. And then the last place that they're asking me about is at 35 milliliters, which is beyond my equivalence point. So again, this kind of gives me a roadmap for those calculations. And so just to save time, I've got those worked out here for you, but we'll talk through each one. So the first thing that's going on there is I just have a 0.1 molar acetic acid solution, and I've done 1,000 of these. You've done almost that many. So all this is a Ka problem at this point. Now, if you'd started with a base, of course, it'd be a Kb problem, but we'll deal with that a little bit later. But for now, a Ka. So what's going on in the beaker at this point is a weak acid equilibrium. My acetic acid is dissociating into some of the acetate ion and some of the hydrogen ion. I start out with 0.1 molar minus X plus X plus X. Again, that same calculation that you've done over and over and over. So I take the Ka for acetic acid. I set that equal to X squared, because those are my products, over 0.1. I'm going to try to ignore that X, which works out just fine for this one. And when I solve for X, I get 0.00134 molarity. That X, again, is my hydrogen ion concentration. So to find the pH, I just take the negative log of that molarity and get a pH of 2.87. Not too bad. Okay. Part B of the question says, what's the pH after I've added 10 milliliters of the base? If I look at my graph, this is, again, that buffer zone that we talked about. The pH isn't changing all that rapidly. And since I'm in the buffer zone, I can use this equation to make my life a whole lot simpler. pH equals pKa plus the log of base over acid. Concentration of base over concentration of acid. That's your Henderson-Hasselbalch equation. The trick here, or the challenge here, is finding which is your base, which is your acid, and figuring out that, that ratio there. So the first thing I'm going to think about is the actual reaction that's happened here. So there's the acetic acid, and this is the hydroxide from the sodium hydroxide. The sodium is just a spectator ion. And notice I've got numbers filled in here that don't match anything that was in the problem. Because this is a BCA chart, I have to use moles. So here is where I calculated the moles for each one. Both of these are 0.1 molar solutions. So that's what this is, 0.1 molar. For the acetic acid at this point, I had 25 milliliters, which is 0.0250 liters. If I multiply those together, liters cancel out, and I get 0.00250 moles of the acetic acid. So that's what's going right here. For the sodium hydroxide, I had the same molarity. I multiply by its volume to cancel out the liters, and I get 0.00100 moles for the hydroxide. So that's where I got that number. So in this calculation, or in this reaction, everything is in a 1-to-1 ratio. That makes it handy. So if I look at these two, I have a limiting reactant. And since they're 1-to-1, the limiting reactant is going to be the one that's the smaller number, which here, of course, is your hydroxide. So on the change line, I'm subtracting out the 0.001 in the reactants, and I'm adding that to the products. So this is what's left over, or not left over really, but this is what remains. I guess the same thing, isn't it? This is what's in the beaker after the reaction has finished. And so this is a buffer solution. This is an acid, and this is the conjugate base of that acid. And so I've got a ratio of base to acid. So at this point, I'm just going to plug into the Henderson-Hasselbalch equation. pH equals pKa plus the log of the base concentration, 0.00100 moles, over the acid concentration, 0.00150 moles. Now, if you are really thinking about this and paying attention, these are concentrations. These are not. I could make these into concentrations, but it doesn't really matter because they're in the same volume. If I divide by the volume here and here, they cancel each other out. So I can just leave these as moles at this point. Now that's not always the case, and I'll show you that in just a little bit, but for this one it is. So pH equals pKa. Remember how to do pKa. It's the negative log of your Ka, which was 1.8 times 10 to the negative fifth. So 4.74 plus the log of 0.001 divided by 0.0015, 0.667. So take the logarithm of that number, add that to 4.74, and you get 4.56. And so if you think about what your calculations are here, we know it's got to go up. I started with 2.87. I end up with a higher pH. Now, the second point that we had in that buffer zone was at 12.5. And this is not asked about in the book, but I added this one in here because this is sort of a special case along the way. And if I look at this titration overall, and I know my end point, I've got it probably skewed over just a little bit, but the equivalence point is at 25 milliliters. This is exactly half of that equivalence point. So I don't really have to do an extra calculation here if I can recognize that. I just want, and like I said, I'm bringing this up just to kind of show you a shortcut here. So only for this one unique point in the titration at the midpoint, your pH is equal to your pKa. And we just figured out that the pKa was 4.74. So I know at that point my pH is 4.74. Why is that true? And it's just simple math. If I'm at the midpoint of the titration, whatever the amount of acid is, no matter what I started with, that's going to equal the amount of that conjugate base. And so if I'm adding the log of acid over base and they equal each other, so in this case it'd be 0.00125 over 0.00125. This is going to be the log of 1. And if you get out your trusty calculator and you find the logarithm of 1, it's 0. So it doesn't matter what you start with. At that midpoint, since acid concentration is equal to base concentration, the log of 1 is 0, and so pH is equal to pKa. Now you could go through exactly the same type of calculation that we just did for the 10 milliliter base, and you would get this, but this is just to save you some time doing that. Okay. I'm looking at my time here. I've got a 15-minute limit, and it's probably going to take a little longer to do my equivalence point. So I'm going to end this video here, and then I'll do a second video to show you how to calculate the equivalence point and beyond. So I will see you very soon.